Uh, so we're working on binary. So I'm Sahil and this is Daniel, and we're going to be working on binary weight neural networks and implement that in VHDL. The same strategy. We're going to train a model offline, get the weights, and binarize them and implement that in VHDL to get quick inference. Only forward propagation, no back. We're not implementing backward propagation. Just letting the you get me. Okay, so over the years, there have been convolutions, recurrent neural networks, Boltzmann machines that have been postulated. And yeah, a lot of our colleagues here are working on LSTMs. It's because they work and they're great for time series data, which is great on the edge. And we all know that edge, the hardware is always a constraint, right? The resources are a constraint on the edge compared to the data center mentality. So, but still, fully connected layers still work and like simple regression problems. They work for like simple image classification, object detection. So we plan to go with that for simple. So we are targeting an image classification problem. So it essentially comes down to this equation where W is the weight matrix, X is the input vector, and B is the bias. And this gives us our prediction for which we compute the loss. Then from the loss we fetch the gradients and we adjust our weights. So that's path propagation. So, but matrix multiplication is the most expensive part here in while we're computing the gradients. So, and this is because GPUs have come into picture because they're quick in those things, right? Compared to like CPUs. CPUs are like they perform more specified tasks, but for generic redundant tasks, GPUs work and they have like a lot more cores than compared to a conventional CPUs. So, uh, yeah. So we have like if you want to implement deep learning on low-level devices, there are certain challenges like with respect to the scalability and the cost. So there's the power. The power is a constrained resource because a lot of these sensors are operated via battery, or on the edge there's just limited capacity. Then so is the storage and the compute capability of the devices. Like you can't expect a Raspberry Pi to perform same as the servers in our data centers. And there's always a communication overhead, especially if the application is distributed. If the nodes are distributed and they're communicating with each other for learning or for inference, there's always that network cost. And then the cost is actually in the sense of the high cost of designing, manufacturing these chips, and the maintenance required, and hardware level optimizations usually come at the cost of droppings and test accuracy. So parallel efficiency against statistical efficiency, it all comes down to just trying to trade off in these two things. So we propose to reduce the layer-wise floating point operations to that of binary. This work has already been done. We've cited the reference at the end of our slides. It's called binary networks, but this was done almost 5 years back, and it was implemented on a fully connected layer. So we are just kind of trying to refresh that in 2020. Gonna use TensorFlow. They did not use TensorFlow back then. Maybe it wasn't open source in 2015, I guess. Don't remember exactly. So
yeah, so we intend to implement network first in TensorFlow, and then like go the normal way as he previously explained, and also look at explore binary weights. The idea is to be able to come up with a hardware which performs simple operations like calculating the two complements of numbers. That way, we can reduce our network into only adders, yes, and subtractors. So the schedule is to review existing paper and also implement. So we anticipate that the literature review is going to take like a week, and also implement our network in TensorFlow, and also get the weights. So we are looking at the normal one and the regular one, and recording its weights, and also looking at certain parameters like the accuracy of that network. Then we are also going to implement the binarized version, and also record the weight and calculate the accuracy, just to have an idea of how much we'll be losing in terms of accuracy. Then we'll move forward to implement the binary network in VHDL and hard code the binary weights in there. So our major cost, what we are looking at, is entirely is mainly based on the accuracy. That's because we fear that we may have to pay so much that our final outputs will not be applicable in a bedded world. So we are looking at how much we are losing by using the binary weights. The time permits, we also will explore how much the resulting hardware performs in terms of time against if we were to implement it the ordinary way. These are the paper that we'll be looking at, and also previous implementations that we came across. Thank you.
Yeah, also, we did not give an explicit work distribution because we're just kind of mixing it together and doing it as we go along. So, we didn't think it was like kind of, because we're not experts in VHDL, so we both might be, collaborating together. So it's like we just done 50-50 throughout all of it. So.
Okay. I have no question because I'm very, very familiar with this project. Okay. Thank you.